I will talk about new algorithm, new accelerated first-order method, and this is a joint work with Lorenzo Orecchia. So the setting for this talk will be the standard setting of first-order convex optimization. We will assume that we are given some convex function, and we'll further assume it is continuous and differentiable. And we want to minimize this function over some closed and convex set. We don't really need to explicitly know the function. Instead, we will learn about the function through a first-order oracle. What this means is that there is a black box, and if we feed some point from a feasible set to it, we get back the gradient of the function at that point. It is possible also to assume that we can get the function value, but for our work, this is not really necessary. To keep things simple, throughout the talk, I will be assuming that the function is smooth. The results also generalize to other settings, and if you're interested in this, please see our paper. So now there's nothing new really about this setting, and people have been working on different variants of these problems for at least decades. And there are optimal methods that are known in many different settings. So for example, we have Nemirovsky's mirrored descent for Lipschitz continuous function, Nesterov's accelerated method, Frank-Wolf methods, and so on. The reason why these methods are so interesting, especially now when we are dealing with very large data sets, is that their typical per iteration complexity is near linear in the problem size, and typically we do not need too many such iterations. However, what I feel has stalled the progress to some extent is that if you look at the classical analysis of these methods, they often appear very unintuitive. It seems like you're just performing some algebraic tricks. For us as the TCS community, the ideas from first-order optimization have actually led to some improved algorithms for various fundamental problems, such as for max flow, packing covering LP, submodular maximization, and many others. So what this work focuses on is giving a unified analysis of first-order methods and a more intuitive approach to acceleration, and also a new accelerated algorithm. So let me now describe you the general framework. So the first ingredient of the framework is the upper bound. Now, this is a minimization problem. So if I take the function value at any point, that's a valid upper bound. It upper bounds the minimum value. That's like almost trivial. So some upper bounds that we typically work with in this framework will be the function value at the last point seen by the algorithm, or just some convex combination of function values at all seen points by some time t. For this talk, we will deal with the first choice. Now, what is more interesting in this framework is the construction of a lower bound. We know that a function is convex. What this tells us is that if we are given a point and a gradient at that point, we are at the same time given a lower bounding hyperplane. This just means a linear approximation of the function lies below the function. And this can even be used as a definition of convexity. So if my algorithm, whatever it is, constructs some points, at each point, I get a new lower bounding hyperplane. And in particular, I can take any convex combination of all the lower bounding hyperplanes I have constructed so far. So this complicated expression is really just saying I'm taking a convex combination of those lower bounding hyperplanes, and I just wanted to use the same notation whether I'm doing this in continuous time or in discrete time. So I have some measure alpha that can be either continuous or discrete. Now, if you look at this expression for a lower bound, there are at least two issues with it. The first one is I don't know what the optimal point is. I don't know the minimizer. I'm trying to determine it. So it's not really telling me much. What I could do is take a minimum over the feasible set on the right-hand side, but this still wouldn't be a very good idea because in general it wouldn't really behave in a controlled manner, and in some cases it may just give me a trivial value of -infinity, which is just not useful at all. So the way to deal with this is regularization. What this does is we add some nicely behaved function. The very least it needs to be is strictly convex, and we add it to both sides. This A of t essentially will be something that determines convergence, so this is a strictly increasing function. So another way to think about it, is not just regularization, is this homotopy approach where we are instead constructing a lower bound on some function approximation. And then as this A of t increases, we actually approach our original function. So now if to deal with the first issue we had, which is to remove this x star, we can now take the minimum on the right-hand side. And if this function, as I said, is strictly convex, this lower bound will behave in a continuous manner as I add more points to construct the lower bound. So this is just my lower bound up to like this correction for what I added to my function. Not 100% precise. This is what we use in discrete time. In continuous time, we need one little more thing just to guarantee that it is defined at the initial point. But that just requires mixing in one more point. So I don't want to make this too detailed. So now I have an upper bound on my optimal function value, and I have a lower bound. So I have an optimality gap. And the basic idea is actually quite simple. This is the main idea. If I can show that my gap multiplied by some strictly increasing function of time does not change over time, then I immediately get that my gap reduces at rate alpha of t. So if alpha of t was a quadratic function, my gap would be reducing at a quadratic rate. Are there any questions so far? OK. The last thing we just need here is to show that the initial gap is not too large. What happens for this framework is that the initial gap just turns out to be some notion of initial distance to the optimum. And now this will be enough to construct the method in continuous time. This is just a little bit of notation. So this minimum is just the minimum we had in the lower bound. And I just introduced notation for the argument of the minimum. So now if I take this time derivative of the scaled optimality gap, I get some inner product between the gradient and something else. How can I make this 0? Well, I make this something else equal to 0. And if you just transform this equation, what you get is an actual dynamics that dictates how your current solution should be updated. And this sort of updates actually make a lot of sense because if you integrate both sides, what this actually means is that your current solution is some convex combination of the initial point and these arguments that we get from the lower bound. And this is, in fact, an accelerated continuous time dynamics. Now, a similar continuous time dynamics was also obtained in previous work by Christian et al. They take a different approach. They actually start with the dynamics and then analyze it using Lyapunov-based methods. This is an opposite approach. We actually just use arguments, and we get the algorithm from the analysis. I should mention that our approach seems easier to generalize because we have managed to generalize this to almost any first-order methods we have seen so far, and also to some non-traditional settings, such as when gradients are corrupted by noise, which is something I'll talk about towards the end of the talk. OK, so we have a continuous time algorithm. But if we want to implement something, we really need to be able to implement it in discrete time. So what do? We use some discretization methods. So in the discrete domain, this argmin, because it's not actually described by differential equation, it essentially looks the same. You just replace the integral by a sum. What we really want to discretize is how our current solution changes. Now, one thing to observe here is that this v of k is supposed to be updating simultaneously with xk. So it depends on the last point seen by the algorithm. And why this is important, I'll tell you in a second. So there are two basic discretization methods. The first one is forward Euler discretization. So here what we do is we update this x of k based on the information up to the iteration k minus 1. So everything is known. What happens when we do this is that we incur a positive discretization error in the optimality gap. So this is something that would slow down the convergence. Now, another method is backward Euler discretization, where x of k, in fact, depends on v of k. But I already told you v of k also depends on x of k. So this is something that is only implicitly defined. In general, we cannot get it in closed form. What is nice about it is if we could implement it, it incurs a negative discretization error in the gap, which is better for the convergence. So what do we do about these two discretization methods? For forward Euler, we can interpret Nesterov's method as performing forward Euler discretization and then doing a gradient step to correct the discretization error. This happens because the gradient step reduces the function value, so it reduces the upper bound, and therefore it reduces the gap. Our idea was to actually take advantage of the slack we get from backward Euler, like this negative discretization error, and we show that it actually suffices just to take two fixed point iterations. And what is nice is that both of these algorithms guarantee the optimal worst case 1 over k squared convergence rate. Now I'll talk a little bit about the comparison between the two methods. So first, let me show you like a quick illustration. So in continuous time, this is how the algorithm moves through the feasible region. This is an illustration of Nesterov's method, and this is an illustration of our method. I'm not sure how much you can get from here, except that you can see, at least in this example, that these two algorithms in general take different paths. They construct different sequences of points. Now, a few numerical experiments. The setup on which we chose to illustrate the results is a known hard instance for smooth minimization. The known hard instance is just a quadratic function where this matrix A is a Laplacian of a cycle. For people who are familiar with electrical flows, this is the same as solving electrical flow on a cycle. And we look at two settings. One is just unconstrained region, and this is just one choice of B that works. And another one is a probability simplex, so that we can see also what happens in the constrained region. To make things more interesting, we also consider some additive Gaussian noise on the gradients. And this is a setting that is interesting because often when you want to implement algorithms, what happens is that the gradients are only estimated from some measurements. So you could be assuming that you're not getting exact gradients, but something that is corrupted by Gaussian noise. There are also cases in differential privacy where we intentionally add Gaussian noise to the gradients. Now, in the case without noise, you can see that the performance of Nesterov's method AGD and our method AXGD is almost unindistinguishable. They give the same performance, and I'm here also showing a slower algorithm gradient descent. Now, another thing that is sort of interesting about our framework is that it explains these ripples we normally get in the convergence of accelerated methods. So what we get in the convergence of accelerated methods is that our function value goes up and down. But the reason this happens, if we look at the optimality gap, this approximate optimality gap, is that we are reducing the gap overall. So when our function value increases, it means that we are actually also improving our lower bound. In the case of a probability simplex, for Nesterov's method, that's not exactly like monotonic decrease. This is an artifact of discretization. Now, when we add noise to the gradients, in the unconstrained case, the two methods really look quite similar and not so great. But what is interesting is that there are some cases, especially in a higher noise regime, where AXGD, in fact, has both lower mean and lower variance. So it seems like the fact that we are kind of averaging out more. Instead of correcting the error, we are taking two identical steps. It seems to help with dealing with additive noise. Now, in summary, what I talked about is a new interpretation of acceleration and general framework for the analysis of first-order methods. The framework also leads to a new accelerated method. The method matches the worst-case complexity of Nesterov, and in some cases, it is more stable to noise, like if we add noise to the gradients. So some future directions that we are already taking, and we have some preliminary results, are getting a formal characterization of approximation error when we add noise to the gradients, and also some approaches to dealing with it and reducing the noise. Another direction is the extension of these techniques to some other settings, such as block coordinate descent and stochastic methods. Thank you for your attention, and I'm happy to take any questions.
Compared to the stability to noise of simpler methods like gradient descent?
Oh, it depends on the setting. Okay, so wait. In this case, well, this implementation is gradient mapping. It seems more stable, whereas in another case, gradient descent is more stable. This is something actually we are kind of investigating analytically. So what is kind of interesting, you see that these methods kind of initially converge faster, and then they just stabilize to something that has kind of high mean and variance, whereas gradient descent just keeps going. So we were looking into, first starting with this fast convergence and then just switching to a slower sequence to get lower mean and variance. Anyone else? Okay, good. Thank you. Yes.
Give us in a noise-free case. What did the hard case? You were saying a little bit about what the hardest cases look like. Do you have any intuition for like why? What is it that's making them hard?
It's a cycle. It takes a while for the information sort of to propagate because you only have access to the gradients, so how things are coupled, it takes time to learn that. So this is an instance that is kind of classically used to prove lower bounds.